We now take our final look at the cross product in this video, which should be a relatively short video, and it's going to be an application of the cross product that's related to volume. So we know that if we have a parallelogram, right? So if we have a parallelogram, and a parallelogram is it's a quadrilateral that has two pairs of parallel sides. And if I happen to know the vectors that define two essentially concurrent sides like this, u and v, right? Then we showed that you can find the area of this parallelogram by computing the cross product of the vectors u and v, and then computing the magnitude. And this is a two-dimensional problem because you're finding the area of this two-dimensional shape or region. Well, there is a three-dimensional analog of a parallelogram. In fact, let me write the word parallelogram here. Now, suppose this was the base of some box that then had some height. So suppose I had three vectors that were like this, and let's say like that, right? And then I am going to, so I'll make a parallelogram out of this pair, like that. Then make a parallelogram out of this pair, so like that, kind of. And then a parallelogram out of these pairs, so, oh, actually, no, that part, I'm really off with that one. So this should be more like that, and then like that. So essentially I'm creating this box, but it's not necessarily a rectangular box. It's a box that's like, it's kind of skewed, like you take a rectangular box, and then you just kind of push on one side of the box to kind of have it slanted, right? So this type of three-dimensional shape is called, get ready for this, it's a parallelepiped, right? So parallelepiped, basically a box that's defined by three vectors now. So let's say we have, I'll call this one u, this one v, and then this one that gives its height, basically, let's call that one w, right? So obviously we would want, so this is kind of the setup. We have u, v, and w. These are vectors in R3, and they're all non-zero, right? So they all have magnitude and length, and they are concurrent, right? What we would like to be able to do is to find the volume of this box, right? Now, the easy way to look at it, to say, well, if this were a rectangular box, right? If this were a rectangular box, I would just essentially take the area of the base and multiply it by the height, right? Well, let's think about it. The area of the base, if I were to compute it in vector form, it would be this, right? I would just have to take u cross v and then do the magnitude essentially. But here's the problem. So let me write down u cross v, and let's think about this for a second. When I do u cross v, I get a vector. And then if I take the magnitude of that vector, I get a number. If I take the number, which is the magnitude of the cross product, and multiply W, I would be taking a scalar and multiplying a vector. So I would be getting another vector. But that's not what I want. I want my volume to be a number. In fact, I want my volume to be a positive number. So this is what we do, right? And again, this is just kind of an informal, intuitive explanation of the proof. The formal proof uses projections and so forth, and it gets a little messy. But I want this to be a quick and easy video, right? Not too messy. So this U cross V is a vector. So if I were to multiply this vector, right, by my W vector, then I could argue that that would give me my volume. But how do I multiply two vectors in such a way that I get a number? Well, that's where the dot product comes in. So basically, if I take U cross V dotted with W, this is now going to give me a scalar, right? Because the cross product is a vector, and W is another vector, and then I am doing the dot product. The only other thing that we have to be careful of is when I do the dot product, my answer might be negative, right? And we've seen it where sometimes depending on the angle between the two vectors, the dot product might be positive or negative. But I don't want my volume to be negative. So what we do is we end up taking the absolute value of this expression, and that gives me the volume of my parallelepiped, right? There we go, right? So there I just kind of gave you the intuition behind this particular formula, and let's just do an example illustrating how it's used, right? So here's our example. So let's find the volume of the parallelepiped defined by U equals 1, 1, 1, V equals -2, 1, 0, and W equals, let's say 3, 1, -2, right? So these are the vectors that defines these three edges, right, of this parallelepiped. Once you have those three vectors, then we apply this formula. In fact, I should say something about this expression that's in the parentheses. The expression, not in the parentheses, in the absolute value. The expression in the absolute value is often called a scalar triple product. So this is often called a scalar triple product, right? Because you're multiplying three vectors, right? Hence triple. But the net result, the end result, your answer is going to be a scalar, right? Let me write this more clearly. So here's scalar triple product, right? Okay, so let's go through and do it. So order of operations, you do what's in the parentheses first. So we're going to do our cross product first. So U crossed V. I will set that up as my 3x3 determinant. So we will have, so in this case, 1, 1, 1. And then -2, 1, 0, right? So we'll have that. Now, let's go ahead and I'm going to write out and I'll do this in the angled bracket form. So I'm going to write something without simplifying it too much, right? So when I block out the first column, I'll be left with 0 minus 1. and then that middle component has to have a negative sign. When I block out the middle column, I'll have 0 minus -2. And then when I block out the third column, I end up getting, let's see, 1, and then minus -2, right? So that's the vector. So this is what I would end up getting just by doing the cross product. But then remember what you would end up to then do the dot product. I would have to take these components, right, and multiply them by the coefficients. The corresponding components in W, right? So I'm going to end up doing 3 times this, and then 1 times this, and then -2 times this, and I would add them all together, right? And it turns out that, so let's go ahead and simplify this, and then we'll do our dot product. So we'll have -1, and then this is -2, and then this is a +3, right? So that's the cross product. Now let's do U cross V dot with W. So that's the dot product of -1, -2, 3, dot, and then W is 3, 1, -2. And then this is where we're going to get our scalar. What is the scalar? Let's see. So it's -1 times 3 plus -2 times 1 plus 3 times -2. Again, just multiplying the corresponding components. I can even highlight it or indicate it here. So those two get multiplied. These two get multiplied. And these two get multiplied. And then we add them all together. But if you notice what's going to happen, we're going to end up with a negative number. We have -3 minus 2 minus 6. So this is a -11. And again, it doesn't really make sense to have a negative volume. The reason why it's negative, it just happens to be, it depends on how the angles are oriented. What is the angle between them, right? And then, so therefore, our volume is the absolute value of this. So our volume is the absolute value of -11, and that is +11. And in this case, it would be units cubed. So there you go. Pretty sweet, short and sweet application. Another use of the cross product, and this allows us to compute volumes of these fancy objects we call parallelepipeds. Say that 5 times fast, and I'll see you in the next video. But don't hurt your tongue. See you then. Bye.